Good morning. I'm Cameron, and I'm here with Victor to give a presentation on our alternative design of the violin bow, as well as some background information on how the violin bow functions.
Today we will be discussing how a violin works with an emphasis on the bow, and then we will be mentioning our project idea.
How a violin works. It is very important to have a fundamental understanding of the instrument we are working with before designing improvements. As a musician plucks or slides or bounces the bow across the strings vibrate. The vibrations travel through the bridge to the top and bottom plate, which then reverberate through its hollow body, producing a rich sound. The strings of the violin vibrate in a circular motion, creating the tone. The vibrations, however, produce the overtones. Within the hollow body, the sound post connects the top plate and the bottom plate and is in line with the bridge. It functions as a conductor for vibrations between the top and bottom plate and improves the structural stability of the hollow body. Due to the nature of our project, the structure that we are most concerned with is the bow itself, and its two major components that influence the vibrational movement, the bow stick and the bow hair. The bow stick is the literal backbone of the violin bow. High-quality bows exclusively use Pernambuco, a Brazilian hardwood that has low damping. Pernambuco has a high density of 800 to 1,000 kilograms per meters cubed and a Young's modulus of 15 to 22 gigapascals. Multiple research papers have come to the conclusion that the stiffness distribution along the stick is the primary influence on playing properties. Experimentation revealed that the bow is stiffer near the tip and the frog than in the middle. In the same paper, it was also stated that the bow was found to be softer with the hair under tension than without. The tension of the hair straightens the stick, and the resulting bending strain helps to restore the curvature of the stick when under load, which is when it is being played. However, the study was not able to draw conclusions on whether or not the stiffness determined the quality of the bow. The image to the right depicts the first 7 in-plane bending modes and their respective frequencies of a straight violin stick with a frog attached. There is a strong relationship between the bending waves of the stick and its torsional and longitudinal vibrations. Many studies, after extensive experimentation, have concluded that the movement of the bow stick is the component with the most impact on vibrations within the entire bow, which is helpful when determining further properties of the bow. Violin bows are classically haired with horsehair. Since the hair has to be a specific thickness and coarseness, the hair is taken from very few breeds found in northeastern Asia, and only a small fraction of the harvested hair can be used for violin bows. The raw hair is dressed by cleaning, combing, and sorting into different qualities and lengths. Horsehair has an incredibly defining mechanical properties. The diameter of the bow hair is typically between 0.2 of a millimeter and 0.05 of a millimeter. The Young's modulus is between 4 and 7 gigapascals, which is similar to synthetic polymers like nylon. The hair is elastic and can take up to 4 to 7 Newton loads. However, bundles of hair can withstand far greater load due to being evenly distributed across multiple hairs. The coarseness of horsehair can be attributed to its strange surface. The rough surface of hair has overlapping layers of scales, allowing for extreme friction when pulled across violin strings. Furthermore, due to hair being a biological product, it has unique chemical properties. Horsehair has a protenic fiber made up of protein keratin, which is capable of attracting other substances, such as rosin. The quality of the violin bow is characterized by musicians through 2 primary factors: playing properties, or the way the bow can be controlled while playing, and the tonal qualities, the influence of the bow on the tone quality. The most important evaluation of the bow is how it moves. The vibrations of the strings and the hairs of the bow and their unique interaction with each other are instrumental to the violin's ability to make such beautiful music. The violin player has the greatest control over the interactions of their instrument. Through control over the bow velocity, force, and the distance across the bow bridge, they have the ability to massively control the sound level and the timbre the violin creates. The bow velocity and the bow bridge distance work together to determine the amplitude of the string vibrations, and subsequently the sound level. The bow force has no perceivable influence on the amplitude of the string vibrations. However, bow forces work alongside bow bridge distance to regulate the harmonics of the note played. The vibrations in a bow can be categorized into 2 directions. Longitudinal follows along the length of the bow, and transversal describes the vertical and horizontal movement outside the plane of the bow, as can be seen by the diagram. Through experimentation, it was found that the longitudinal admittance typically displays resonant peaks below 4,000 Hz. The highest peaks, which fall in the range of 1,500 and 2,000 Hz, reach an admittance level of 0.5 seconds per kilogram. In the transversal direction, the admittance is much higher, at about 10 seconds per kilogram at the resonant peaks. The admittance of the stick alone, without hair, as measured in the longitudinal direction, is similar to the admittance measured with the hair. This applies to both admittance levels and resonant frequencies. Since it is a common trend in various studies, it can be concluded that the bow stick is the most impact on the movement of the bow as a whole. Furthermore, it was also observed that when the bow was pressed against the string, no major changes in admittance occurred. The bow is a device of high impedance compared to that of the string, and consequently, the string load does not induce a major change, encouraging the theory. Conversely, the transversal admittance is influenced by the tension of the bow hair in many ways. The frequency of the hair mode changes from normal value in the vicinity of 65 Hz to above 80 and below 50 Hz, which is either side of a range of extremes when playing tensions. While the overall admittance level changes only a little with tension, the curves become much more featureless when the tension is brought down because of the number of resonances decreases. Knowledge of how the violin generates its specific frequencies and movement are quintessential when improving or creating a new design. These properties are goals that we strive to achieve with our new design, especially in order to make our new design viable alternative to the current system that has been cultivated over the past several centuries.
The main purpose of rosin is to increase the friction between the bow hairs and the violin strings. This figure refers to an experiment in which 4 different types of rosin were used, each with a different coefficient of friction, and of course all those coefficients of friction being greater than the bow hairs with no rosin. In this experiment, the frequency spectrum was recorded for each of the different rosins, and while they are similar, you can clearly see that the amplitude is lower in the higher frequency range for the highest coefficient of friction rosin. We will now discuss our project idea. Sticking with the current design for violin bow hairs has a lot of positives. It's already designed, it produces the desirable sound, has a unique scaled structure that is hard to mimic, and the single hair breaking does not ruin the sound quality of the entire bow immediately. However, it can be very difficult to rehair a bow, especially for the inexperienced. Violin bows also require a lot of horsehair, and this hair is not ideal in every way. It is very dependent upon humidity, making it hard to play in different environments. Also, being hair, it is thinner and therefore weaker at the tip. While it is unreasonable to expect the new design to have none of the cons and all the pros of the current system, there are definitely features which can be improved for certain audiences. One of the main things we want to look at improving is ease of rehairing. One of our ideas for this is using a single strap. If we're able to match the coefficient of friction, this would potentially allow for easier rehairing as only a single strap needs to be dealt with. Depending on what material we're able to get to work with this could also be cheaper. The one thing we want to look into more is the keratin-based textile. This is something that can be 3D printed, and because it's keratin-based, it would have the benefit of acting like horsehair in lots of different ways. This could be a negative, but it's something that should definitely be looked into. Another negative with using a single strap is there would likely be less, or at the very least different, control over the instrument, as tilting the bow would not have the same effect.
Here are some rough sketches of potential designs for an easy-to-hair bow. The hair is already strung together with the frog side pre-bracketed so that it can be easily screwed into the frog. The opposite side of the hair grouping is placed into a plastic encasing made to fit into a groove or spring latch located at the tip of the bow. Then the hair can be pulled to the tip of the bow and snapped into place on the bow stick easily and effortlessly, while also maintaining the tension in the string.
Here are our references, starting with our scholarly sources and then our non-scholarly sources.